Yeah, no, that doesn't look right. Welcome back to Cloud 42, I'm James. This video is part 3 in my series on building an electronic lead screw for my lathe, which is a device that replaces the change gears with a motor and a controller so that I can change threads and feeds just by pressing a button instead of messing around with the change gears. Today we're going to take a look at the control panel, how that interfaces to the microcontroller, and some of the things that I had to do to get it to work. This is the prototype of the electronic lead screw that I showed in a previous video. And again, this is the TI microcontroller board. This is a launch pad. And then this is the 7-segment LED display board that I chose and showed in the previous video. We've got an encoder and a stepper motor. Now, I got a bunch of comments on the previous video about how I was going to need a much bigger stepper motor because this is the stepper motor that I was using for the proof of concept on the bench. And yes, I'm aware that this little stepper motor is not going to turn the lead screw on my lathe. This is the stepper motor that I'm planning on using. And I'm also looking at possibly using a servo, and I've got one of those ordered, and we'll look at that in the next video. Now, I've gotten a bunch of comments about this LED display board with this little button panel, telling me that this was just not going to be good enough, that I really needed a color touchscreen LCD. Yeah, maybe. And I actually have ordered a color touchscreen LCD, and I will be playing with that. But for now, I'm continuing with the original concept. When I decided to use this board initially, I selected it because I had a very specific idea in mind for how I wanted the user interface to work. I was looking for something very simple, something that was very bright and easy to read, that I could see while using the machine tool, and that wasn't going to be susceptible to, dirty fingers or damage from vibration, or, something that I was going to be worried about breaking in the shop. So my idea was to take this little board and put it in a die-cast aluminum bud box. And this is just a small box from Bud Industries. These are die-cast aluminum. They come in a whole bunch of different sizes. But this is about the right size to put that board inside, make a little cutout for the display, and little lights or little lenses or holes for the LEDs, and then make provisions for the buttons. And the plan is to actually 3D print rubber buttons that will be trapped between the panel and the switches here, so that when you press them, they click through and you get these nice kind of flexible, soft rubber buttons on the front of the case. Now, to design all of that, I didn't want to do this by trial and error. I wanted to do a 3D model so that I could 3D print the buttons, know they'll fit, machine out the aluminum case, and know everything will fit. So I contacted Bud Industries and asked them if they could provide a 3D model for the box, and they emailed one to me. So that allowed me then to take this front part of the case, take the lid, design the cutouts in it to fit the 3D model that I made of this button board, and then design flexible rubber buttons to fit into it. And this is what I came up with. This is just a 3D print of an early prototype of the front panel. So it's got an opening so you can see the LED display through it. It's got a place where I can snap in lenses for the LEDs, and then a place where I can put in the buttons. And these are the flexible rubber buttons. These are printed in NinjaFlex, and they are solid. Well, they're not solid, they're only like 40% infill, but they're relatively solid individual buttons, but they are connected together with these sort of flexible runners on the sides. The idea being that if I press any one individual button, it'll go down and press the switch that's underneath it, but overall they'll stay in place because they're connected together, and I won't have to worry about them twisting or coming out. So I've got some little triangle buttons for up and down and some buttons for the modes. Now, this was the first prototype print, and so they don't fit as well as I'd like. I made some adjustments. These are just a little bit too tight. They press down, but they don't pop back up. So this is the idea. You got up and down to change the setting, and then a bunch of little buttons to change the modes, a smaller button to access settings, and the button on the left for power. Now, the other thing that I need to do is cut an opening in the end of this for a connector. And so I just grabbed the model for the back half of the box and cut out an opening, designed the opening for it so the connector would fit. Made sure that all my clearances inside were going to fit because I had a 3D model of this board and the connector. And so I got it all together and I was getting ready to go mill the front of the case, and I realized I don't even have to do that. I can just 3D print the bottom half of the box too, and I can make a prototype. Now, in the future, I'm going to want to do it in the metal, particularly so that I can come back and engrave the markings in the front, maybe even fill them with paint, I'm not sure. But I'll put up on the screen here a diagram showing where the labels are going to be and how this is going to work. So you can look at that, but for now, for today, you'll just have to imagine it. But since I can 3D print all the parts, including the box, I went ahead, the only real thing I took were the screws, and actually built up a prototype. And here it is. So I've got the box, and you imagine this will be aluminum. It'll have the markings engraved, and then it's got the flexible buttons that are nice and easy to print. The up and down buttons, it's on the last button and the third to last button. This middle one's not used, and that gives a little bit more space because these are going to be the keys that are going to be pressed most often on the lathe to go up and down and change the settings. And then a button for English and metric, a button for thread or feed, and then a button for the direction. The small button is for settings, and then the left button is for power. So let me do a little demo here and kind of show you how I see the user interface working. And this is all implemented, this is all real. So right now, this LED is the feed LED, so we're in feed mode, and the unit LED for inches is set up here. So this is 0.005 inches per revolution. So if I spin the encoder, you can see the stepper motor turning. And I can dial that all the way down to 1,000th, and I can dial that all the way up to, let's see, how far did I go? I think I took it up to 40. And not every value is there. It's just a table, a 35, 30, 26, 23, 20, 17, 15, 13. These are just feed values that I thought seemed like they would be appropriate. And this is just a table in the firmware, so it's easy to change. And you can note that the display here on the left is showing the RPM of the lathe. So as I spin the encoder, you can see the RPM value changing there. I can get it over 1,000 if I flick it really fast. So this next button is to switch to metric mode. So I switch to metric, we're still in feed, and this LED is for millimeters. So this is 0.12 millimeters per revolution. And I can spin the encoder, you can see the stepper turning, and I can dial this all the way down to 0.02 of a millimeter and all the way up to 1 millimeter, which is roughly equivalent to the 40 thousandths that I had on the imperial feeds. Now the next button over switches between feed and thread. So we're in feed mode right now. Click this, now we are in thread mode, that's thread and millimeters because these are metric threads, so 0.5 millimeter pitch thread. And I can go down all the way to 0.2, and there's a table in here of just standard metric threads, 0.2, 2.5, 3, 3.5, 4, 4.5, 1.25, all the way up to, I think, 5 millimeters. So you can see the stepper's really moving on that. And then we can switch back to imperial, and now it's still set to thread, but instead of the inch LED on, we have the TPI LED on because the imperial threads are in threads per inch. So it starts out 26 threads per inch, you can go all the way to 80 threads per inch, and all the way down to, right now I believe I have it set to 8, is the smallest one in the table. And we've got 11.5 if you want to cut garden hose fittings. The last button here is to change direction. So when I'm going this direction, you can see that the stepper is moving the same direction as the encoder. Hit the reverse button, and now it goes the other direction. And so you can just switch back and forth between the feeds and threads, imperial and metric, direction as much as you want. And right now this is just switching live, so it'll suddenly shock and go the other direction, no problem. When this is really on the lathe, that's not going to be practical. There's going to be too much inertia, and we'll want to have some acceleration, or potentially even just have it refuse to change mode until the lathe is actually stopped. Since we have the RPM readout here, we can tell when it stops, and so it'd be entirely practical to say I'm going to switch direction, and it just doesn't switch direction. Either it ignores the button or it toggles the direction but doesn't actually change until you stop it. have to play with it and see what makes the most sense. Okay, now this all works great, but let me show you something funny that I noticed last week. So right now I have this plugged into my laptop over here, and it's getting its power over USB from the laptop. But watch what happens if I plug it into an inexpensive cell phone charger. So I'll plug it in here instead, and then plug this into the plug strip over here where you probably can't see. And we get that. And that is not what I wanted. So I spent a whole bunch of time trying to figure out what was going on. And this is one of those sort of unexpected things. I'd been plugging it into the laptop because I was working on the code, and everything was working great. And then one day I happened to plug it into a different power supply and discovered this. And this would be a showstopper. I mean, obviously I can't leave the lead screw plugged into a laptop. So we got to figure out, why is this happening? I spent a bunch of time. I tried some different power supplies. Every cell phone charger I tried did the same thing. Plugged into my laptop, it worked. Plugged into an external battery, it worked. Plugged into the USB port on the front of my oscilloscope, it worked. But it didn't work at all on a cell phone charger. And so if a lot of people are going to use this and build these, or if there's ever going to be a kit for this thing, it's got to be robust. This is not okay having it be that sensitive to the power supply. So I dug in and figured it out and got it solved. And let me walk through what I found. But in order to do that, I think we need to start with the schematic. This is a schematic showing how the microcontroller is connected to the display board. Now, the display board uses 5-volt logic level signals, and the microcontroller outputs 3.3-volt logic level signals. So it is necessary to convert those. And you've probably seen, there's actually one in here because that's what I was using previously. You've probably seen these little logic level converter boards. These are sold by everyone. This is just an inexpensive import. But what's on here, there's 8 resistors and 4 transistors. And these transistors are BSS 138s. Now those are surface mount transistors. There have been a lot of requests in the comments to eventually have a through-hole kit for this. So I have been playing around with some 2N7000s, which are through-hole resistors, and I have those down here on the breadboard, and it's the equivalent circuit with the actual resistors, through-hole resistors, and through-hole transistors. And this is what's going on. And this is a standard level converter. These are typically used for I2C buses and any place else where you have you just need a simple logic level converter between like a 3.3 volt microcontroller and in this case a 5-volt display driver. This is an N-channel field effect transistor. Now the one on the little board is a BSS 138. The ones that I've got on the breadboard here are through-hole 2N7000s. And the way this works is the line comes in on the source and it goes out on the drain. And the gate is connected to the 3-volt positive rail. And then both sides have 10K pull-up resistors. So both sides will float high. If nothing is attached to it, both sides will be high. And then this is run typically in this case, especially since we're dealing with a bidirectional data line, these are done with what's called open collector or open drain circuitry, which means we rely for a high level signal for a binary 1, we rely on this resistor to pull the line up to the positive voltage rail. And when we want a 0, there's a transistor that comes on inside either the microcontroller or the display driver or the display board that pulls it down and produces that 0. So what's important here is that we have a strong signal to pull this line down, but when it's going up, it's only going up through a 10K resistor. So it's a relatively high impedance and there's not a lot of current available to pull that line up. So if you have any kind of capacitance on the line, which we do, it may rise slowly, depending on what this resistance is and how much capacitance is on the line. So if you've never seen one of these converters before, essentially what happens is if both lines are high, then they're high. If you pull one side low, if we pull the low voltage side, the 3.3 volt side low, then the gate is going to be at 3.3 volts and the source is going to be at ground. And so because the gate is above the ground, above the source, this is going to switch on and conduct. And since we're pulling this side low and this is switched on, it's going to pull this side low as well. So when this is not turned on, this side will be floating up to 3.3 volts, this side will be floating up to 5. So we have our 1 going through the logic level conversion. And when this switches on, pulls this side down, turns on the transistor, and that pulls this side down. So we've converted our 0 on the 3.3 volt side to 0 on the 5 volt side. Now, if the signal is going the other way, and you pull down the 5 volt side to 0 while both sides are floating, the FET transistor has a body diode in it. So if this side is lower than this side, it will conduct, pulling this side down. So if you pull down the 5 volt side, the 3.3 volt side comes down. If you pull down the 3.3 volt side, the transistor turns on, which pulls the 5 volt side down. And so this is great. These are used in I2C buses. These are used in SPI buses, which is what we have here. And they can be used any place where you want to convert from a 3.3 volt signal to a 5 volt signal. And when I say any place, I mean almost any place. There's one caveat, and that is that since this is open collector or open drain logic, there's nothing, like I said, pulling the voltage high except these resistors. So when you have a long line, in this case this is a shielded cable and there's a long cable in here, this actually acts like a capacitor. And so you have a resistance that you're pulling the signal up through this resistance, and it's connected to a capacitor. So what you effectively have is an RC filter. You have a resistance and a capacitance to ground. So if you put in a square signal like this one, a nice square sharp rising edge, through this filter it's going to round off that leading edge, and so you won't get that fast rise. You'll get a slower rise because the current is flowing through the resistor, or in this case this resistor, and charging up the capacitor slowly. So it rises slowly. And so you have to understand what your resistances are, what your capacitance is, so that you understand how long this is going to take to rise and make sure that it's appropriate for the timing of your circuit. Now, to make matters worse, over here on the display board, they've installed a 100 picofarad capacitor to ground as a noise filter. Well, this makes it worse because we're driving through more capacitance and getting more rounding on the signal. Now, I'm also on the output of my board going to be putting in a 50 picofarad capacitor and a series resistor in order to make this more immune to electrostatic discharge, so static shock is less likely to fry the microcontroller, and also to suppress RF noise trying to come in on that line that might interfere with the microcontroller. So all of this turns into signals that are rounded over. Let me power this on and let's look at the oscilloscope and I can show that in action. To start out, let me plug this in to a power supply that actually works. And the reason that one of these supplies works and the other one does not is because of very, very tiny differences. You can see it's not totally stable. It just registered something. Let me hit the one shot on the oscilloscope and you can see kind of what's happening here. So this is the communication between the microcontroller and the display board. So the first thing that's happening is the chip select line goes low to tell the display that something is coming, and then we clock off a byte. There's 8 bits on the clock, and then below that is the data. And you can see the data is decoded here by the oscilloscope as 0, 2. And that is telling the board, the chip on the display board, to go into sequential address mode. Then we send another command. This next byte is telling it, I would like to read the buttons, and then we clock off 4 more bytes, 1, 2, 3, 4, and it reads which switches are pressed, and you see those are all zeros. If I press one of the switches, let me pick this one, just hold it down while I trigger this again, you can see that now there's a 1 bit here. If I let go of the switch, you see that's a 0, press the switch, trigger it again, hang on, and you can see there's a 1. 0 and 1. So this is operating correctly, and if you look at the display, it's operating correctly. And what's happening is this data line is being controlled by both sides. It's initially controlled by the microcontroller when we send these first 2 bytes, but then this data here is being clocked back by the chip. Now watch what happens if I plug this into the other power supply. Okay, so we got the display going nuts again. Let me trigger this. And you can see we've got the same transaction. We're clocking in the sequential read command, then we're asking it to read the buttons, and then we clock off the 4 bytes for the button values. But you see this line stays high. And the reason it stays high is because the display driver chip that's actually processing the key presses did not get the message that it was supposed to read back the data. And so it stayed in a high impedance state and it is not clocking the data back. Now, I went around and around with this. If you look at the data sheet for this TM, what is it, the 1638 chip, I think, that's in here, it says that you're supposed to use it with a couple of bypass capacitors. This board has no bypass capacitors, so I actually pulled this out, scraped some of the traces off the back, put the bypass capacitors on it, thinking maybe I've got too much ripple in the power supply on this little phone charger, and that's the issue. But that didn't do anything. In fact, the bypass capacitors are still on there. And I went around and around, and then I noticed this right here, this little glitch. After that first byte, there's a glitch here on the chip select line. Let me see if I can center that up and make that a little bit wider so you can see it. So what you're looking at here, the top trace is the chip select signal coming out of the microcontroller, and the bottom trace here is the chip select signal as it arrives after it's gone through the level converter to the display board. Now, don't worry about the levels. Those are not the same because I've got the gain set differently on the 2 channels. But it took me a long time to figure out what on earth that little glitch is. And then I realized that's a coding error. What's supposed to be happening here in order for the chip to register properly is we lower the chip select line, send a command, and then raise the chip select line in order to tell it that that's the end of the command. Then we lower it again and send the next command. But that is really, really short. And the reason is because in the code, I had the line of code that raised the chip select line, and then I called the next routine to send the data and just lowered it again, not realizing that those instructions are going to be run one after the other on this microcontroller, and this microcontroller has a 10 nanosecond clock cycle. So that is a 10 nanosecond width pulse. And what's happening is, by the time that goes through the capacitive filter here, but through this RC filter, it's getting attenuated and there's just not enough left of the pulse for this chip to understand what's going on, and it misses it. And so it then sees this next data as a continuation of the previous command, which is invalid, and it doesn't know how to interpret it, and so it never sends the data back. And so that's what's going on. Now, why is this different on one power supply versus the other? The best that I can come up with is the voltages are ever so slightly different. The voltage regulation is a little bit poorer on the cell phone charger, so there's a little bit more ripple, and it's just enough that when it's plugged into a high quality power supply like the one in the laptop, it is registering that, but the conditions are slightly different with more ripple on the power supply, and it just doesn't quite register it. So it was working, but there was no margin. And so this was going to be really delicate in practice on a real machine with real noise. It was not going to be reliable. So what I did is I went in and added a delay. 1 microsecond was plenty, so I think I added 3 or 5. Let me go ahead and put that delay back in and show you the difference. Okay, I put the delay back in, and it looks like we're waiting. Let's see, how long was that? The rise time, I gave it 5 microseconds. So now let me switch this over and plug it into the same cell phone charger here. Plug that in. And lo and behold, it's working. Okay, let me do another one shot over here on the oscilloscope. Now you can see, before I press the button here, you can see this glitch. That's what we recorded last time. Now that should be much wider because it should be 5 microseconds now. So there, I clicked single, and you can see that's now 5 microseconds. And you can see that this is clocking off. As soon as we start clocking this next byte, the line drops because the chip has taken control of the line. So let me press one of the buttons and hit the single shot again. And you can see there's the data for that button. If I push a different button, there's the pulse over there. Hit it again with no buttons. Oops, it triggered on a different point. Now that data is all zeros. So that's all this was in this point, it was a coding issue. Now if we zoom in on these signals, you can actually see the rounding going on in the pulses. So let me just pop over here to that chip select pulse. On the top is the signal from the microcontroller that is nice and square. And then next to it is the same pulse after it goes through that RC filter that's formed accidentally by all the capacitance in the circuit. And you can see that the leading edge of that, especially if I make it wider, is definitely rounded off. It's no longer square. And you can see on the other signals down below, on the clock line in particular, you can see that those signals are all rounded off as well. Now, it's still working just fine because the clock line here drops and the data goes high, and then when the clock line rises again, when it reaches its voltage threshold, that's when the system is then going to read that bit. And so when the clock goes high, this is already high. There's been plenty of time for that transition, so it's still working. However, when we add more cable and more capacitance, this rounding is going to get even worse. So let's do a worst case scenario test and see how that works. Let me grab a piece of cable here. And I have one I prepared earlier. This is 8 conductor, actually 10 conductor, but 8 conductor, 8-pin connectors. And this is 15 or 16 feet of cable, which is more than we will ever need. We'll probably want to run about 2 to 3 feet on the real lathe when this is installed, but I'll go ahead and test with 15 just to make sure that we have a safety margin and this thing is still going to work. Let me hook this up. Okay, I've got this hooked up now. I've just run to the end of the cable. I've got like 15 or 16 feet over here. It's actually wrapped around the motor and the power wire, so that'll be a good test too. And let me plug it in. And there it is, Cloud 42 ELS 1.0.01. And we can go through it with the buttons, switch modes. Everything's working, there's no settings. Reverse, and that is all working. Let's do a one shot on the oscilloscope and see what we've got. Okay, and there it is. You can see the extra rise time on the chip select signal and the extra rise time on the clock signal, but it is getting high enough that the chip is actually recognizing it, and it is pulling this down. And if I press one of these buttons and single shot that again, you can see it is sending the data. And that's not getting all the way up to full voltage, but it is enough that it's triggering. And this is a ridiculous amount of cable. This is more than I will ever use in a real application. Right now, this is triggering, or this is clocking in at 250 kilobaud. I'll probably lower that to maybe 115 or even lower than that. There's plenty of time here in the cycle to do this communication, and it's being offloaded to the serial peripheral, the SPI peripheral, and the chip. So there's not really any problem if this takes a little bit longer. Right now I'm refreshing this thing 100 times a second, and we've got lots of extra time to make that happen. So I probably will slow it down a little bit more to make it even more robust, even though at this speed I don't think we're actually going to encounter any problems, because this really is kind of a worst case scenario test. Well, that's all I'm going to cover for today. Next time we will take a look at the stepper motor that I'm using here, the stepper driver, and the electronics to interface it to the microcontroller. And in addition to the stepper, there have been a lot of comments on the previous videos telling me that the stepper is not going to work, that it's going to lose steps, and it's open loop. I actually did pick up a NEMA 23 servo motor that I'm also going to do some experimenting with, and we'll see if the stepper works well, if the servo works better, and we'll kind of get a feel for what the options are if you want to build one of these for your lathe. Well, that's it for today. If you are enjoying these videos, please give me a thumbs up. Feel free to subscribe to the channel and leave me a comment. I'd like to know what you think. Thank you for watching.